Problem 1 tests you on the different types of combinations of two functions. Part A. This is a simple arithmetic combination of two functions. This one is the quotient, and it is very straightforward. Simply equals to fx divided by gx. Simply finding the quotient of the two functions, and fx is 1 over x minus 1, and then gx is x plus 4. Now apply your algebra to simplify this form. This becomes 1 over x minus 1 multiplied by x plus 4. And you can leave the form like this. If you want to continue on to write the denominator into a polynomial form, you can. This equals to x squared plus 3x minus 4. And that will be the quotient of the two functions. And you can determine the domain of this function from this step. Because the denominator cannot be 0, therefore x minus 1 multiplied by x plus 4 cannot be 0. Therefore, x minus 1 cannot be 0, and x cannot be 1. And also, x plus 4 cannot be 0, and x cannot be negative 4. So x can be anything else except for positive 1 and negative 4. So that's the first problem. Next problem is the composite function f composed of g function. This equals to, you can rewrite this into f composed of gx, and you can evaluate the f function at x equals to gx. Therefore, plug gx into the original fx function, so 1 over x now is replaced by gx, and then minus 1. Just like evaluating the function at any given independent variable value. And then, because gx equals to x plus 4, this further becomes x plus 4 minus 1, which is 1 over x plus 3. So that is the composite function, f composed of g. And the domain of it is determined by, again, the denominator cannot be 0, so x plus 3 cannot be 0. Therefore, x can be any real number but negative 3. The next problem is g composed of f function. This equals to g composed of f function. So again, we start by evaluating the g function at x equals to fx function. So g function is x plus 4, but now x is replaced by fx plus 4. And then, because fx equals to 1 over x minus 1, so this becomes 1 over x minus 1 plus 4. If you want to further simplify this, this becomes 1 over x minus 1 plus 4 times x minus 1 over x minus 1, which equals to 1 over x minus 1 plus 4x minus 4 divided by x minus 1, and then add the numerator together. That will be 4x minus 3 over x minus 1. And again, the domain is determined by the denominator cannot be 0, so x minus 1 cannot be 0. Therefore, the domain is x cannot be 1. Next, problem number 2, to find the inverse functions for the following two functions. The first one, fx equals to 1 minus x squared, and there is a domain attached to this function. It says that x has to be smaller or equals to 0, which tells you that because the domain of the original function is the range of the inverse function. Therefore, from here, you can draw the conclusion that for the f inverse function, the range must be y is either smaller or equals to 0, or f inverse x is either smaller or equals to 0. So with that understood, we follow the 4 steps of finding inverse functions algebraically. First step, rewrite fx into y. Second step, most important step, to switch x and y, so y becomes x and x becomes y. The third step is to solve y from the second step. To solve that, we move y squared to the left, isolated by itself. To the right, we move x to the right, change sign, 1 minus x. Therefore, y equals to, normally when we solve this, we could have 2 answers. Y could be either positive 1 minus x square root, or y could be negative square root of 1 minus x. However, you have to make a decision which one it is. Keep in mind here, we have already come to the conclusion that the range of this function has to be smaller or equals to 0. So because of this range, you know that the first one needs to be eliminated. Therefore, the correct answer is the second one. And after you have made that decision, the last step is simply to write y into f inverse x equals to negative square root of 1 minus x. If you want to, you can use a sketch to help you decide that as well. The original function, when you graph it, 1 minus x squared, the graph should look like something like this. However, you know that x has to be smaller or equals to 0. Therefore, it tells you that it doesn't have the right hand side. It only has the left half of this function. And then you know that inverse function must be symmetric about a 45 degree line, or the identity function y equals to x line. And when you draw the mirror image of the original function, it looks like this. And again, that tells you that the range of this function is that, as you can see, it happens at the lower half of the coordinate system. Therefore, the range of it is y is smaller or equals to 0. That could also help you decide that this one should be the inverse function instead of this one right here. Okay. For this problem right here, we do the same thing. 4 steps to find the inverse function. First step, write fx into y. Next step, always the most important step, change x and y. So now y has become x, x has become y. And then from step 2, we need to solve for y. We multiply both sides by 2y plus 5, the denominator of the right hand side. So x multiplied by 2y plus 5 equals to 3y minus 4. Multiply the left hand side out. 2xy plus 5x equals to 3y minus 4. We want to solve for y, therefore we group y together on the left, and we group all the terms that do not have y together on the right. Therefore, 2xy stays on the left, 3y has y in it, it also has to be moved to the left, and the sign will change. Therefore, on the left hand side we have 2xy minus 3y. 5x does not have y in it, it has to be moved to the right, and it has to change sign as well, so negative 5x minus 4. Y is a common factor on the left. It can be pulled out. Within the parentheses, you will be left with 2x minus 3, and that equals to negative 5x minus 4. Divide both sides by 2x minus 3. You have y equals to negative 5x minus 4 divided by 2x minus 3. Or you can pull out the negative sign to the front, and you will left with a negative 5x plus 4 now, and then over 2x minus 3. And the very last step, again, just change y into f inverse. Okay.